Okay, going live in 5 seconds.
Oh, shit. Okay.
We're live.
All right, everyone. This is another Wolfram Institute live science stream. Today, we're going to be reviewing some initial results that Carlos has produced on subaxiomatic foundations of mathematics. So for those of you who have watched previous live streams, what we're doing as a preliminary exercise is we're taking Boolean functions, and we already know, because Stephen did some work on this a few years ago, that Boolean functions can be nicely emulated with SK combinators with the appropriate setting of true and false values with the combinators. And so I had the suspicion, well, if we can do this for particular Boolean functions, then why don't we, compose these, and then we can emulate arbitrary expressions in Boolean algebra via SK combinators. And once we have those, it would be very intriguing to begin to actually, take these actual expressions as emulated as Boolean, um, take these actual Boolean expressions as emulated by SK combinators and actually evaluate them. They should evaluate down to the correct result of true or false. If you're taking true or false, if you're taking those to be the arguments. But what we want to understand is when you're evaluating from some Boolean expression, you're beginning with something that is a combinator emulation of a Boolean expression, and then you're evaluating down to say true or false, which is also defined in under this particular semantics as a truth or falsity value as emulated via the SK combinator. What do these intermediate states look like? To what extent do the intermediate states still include combinator emulations of Boolean algebraic expressions? And to what extent is it the case that as we emulate Boolean algebra at this highly minimal level, with this very with this quite parsimonious formal system, to what extent is it the case that as we actually, quote unquote, do Boolean algebra at this very low machine level, that what we find in this, intermediate zone is really kind of a collection of emulated Boolean expressions and, unidentifiable kind of machine plaque, or this kind of residue of being of operating at this very low machine level. So I actually don't know, to what extent it will be one or the other, but Carlos has been, and I think with assistance with Nick, has been developing the functionality that will allow us to do experiments. So we don't have, I believe it's the case that there are not experimental results that are fully available to share, but there are some kind of early results, and there's some, and when I say early results, I basically mean there's functionality that's been built, and there are some examples of functionality. So we can look at that today. We can do some preliminary discussion, and then from there, Carlos will go out and just run a whole mess of these, and then we can more thoroughly look at these results under a more precise experimental design. So Carlos, I've really been looking forward to this, and so please go ahead if you want to share your notebook, walk us through what you've been doing. Let's dive in.
I've been looking forward to this as well, because this is my opportunity to share with you two here on the call and the viewers what my concept of the project is and what I think are interesting directions to take it and to design the experiments. So I'm going to do a very quick review of what a rewrite system is. So a rewrite system basically is a collection of rules that apply to some kind of states that can be of many different kinds. You have strings, you have graphs, hypergraphs, you have expressions like in arithmetic, you have abstract algebra, all kinds of things. And so the idea is, as illustrated here, you begin with a particular state, we call the initial state, and then one special kind of rewrite rule that is very common is the motif detection rewrite rule. So it's something that is based on detecting motifs and changing a motif for another motif. And a motif is basically just a sub-expression, like a sub-term of a larger object. And so here's the basic flow of the procedure for anyone who is unfamiliar with this kind of systems. You have an initial state, you detect motifs, you apply the rules, and then you get your resulting states. And so the Wolfram language is actually very well equipped to deal with this, and I've been learning all this functionality, being an avid user of Wolfram language for science, but not for this kind of programming. I had to sort of really get up to speed with these kind of things. So for example, there's a very nice function that was developed by Nick and Ed, is that the name of the other guy?
What, Ed Peg?
Yeah.
Okay. Yeah.
So, and this is in the repository, and it basically displays what. Oh, by the way, so this color code I just have it here is, I mean, just for clarification, not so you don't see.
Yeah, that's nice.
A complete mess
that's nice.
of code. I mean, it's. I think there should be a way to make it automatic. This is manual, but I'm sure it's possible to do automatic. But anyway, so so this is what is produced, right? So if you look at this closely, you see that there is. You take a number, in this case it's going to be some integer, and you add 2 or you add 3. So these are effectively the two rewrite rules. And so this is just, all this code here is just to display +2 or +3 in the right position, right? And basically this tells you that the initial state is 0, and this tells you that you should apply rules up to 4 times. And so you get this natural way of, if you start from 0 and you can only add 2 and 3, which are the ways in which you can get to 10, 12, and 11. And these are the paths. They are on the screen. So in my opinion, it's a great function. Anyway, so because we have in mind that we want to see combinators in these expressions, and we want to detect motifs within large expressions of combinators, I did my own sort of pedagogy of how Wolfram language deals with these things. And I think it's useful for people to see that this is how the machine operates, and that's how we're running our stuff. So most of this is kind of, just my learning, and it's not so relevant. I mean, basically, we take expressions, we look at positions of those expressions, and those are themselves some kind of tree-like structure with brackets and symbols. And then we want to highlight, so this is just some kind of red frame to detect something that is there. We can give different colors. We can have more sophisticated functions that have, depending on what you're detecting, different colors, all kinds of things. And this basically, you use this map add thing to give an expression, just map where the pattern is, right? So this is the simplest expression where you have a position and you have an expression, and you just map it like that.
Yes.
Very simple.
Yep.
So then the function is motif detect, where you basically search for the position where the motif happens and and what you want to highlight in what particular way. And so this just does what you want. You pass it an expression, and you pass it a sub-expression, another expression, and if it occurs as a motif in the expression, it just highlights it, right? Like that's what it does. So in particular, because we're interested in combinator emulation of Boolean algebra, I had to grapple with these functions in this repository function, and this is where I sank most of my time, by the way. I just had to. It turns out this might be a relevant comment for later for actual wiring of the code. I had an issue where the vertical bar and less than and vertical bar and greater than were a different type or something, and my local the cloud one was not processing at all, and I spent hours trying to figure that out. I just had to retype it manually myself because I copied it from some of the notebooks that I had from you. Anyway.
Well, one tip, if you find yourself in that position, I mean, contact, Nick, or contact me for tech support of some kind.
I did contact Nick a few times.
Oh, you contacted Nick. Okay, good.
Yeah.
Okay.
So, okay. Anyway, so this is just testing of this motif detection for the combinator, and in particular, we have also the multi-way combinator, which is another function, but it deals with strings instead of states. So it's a lot of stuff on the screen, but it's basically just testing that. And so this is
okay. You also do it for the multi-way case. Okay, that's nice. Okay,
yeah, multi-way case just basically you have to, I think to expression, right? So you just turn strings into expressions, and then it's fine. I think this is illustrating. Yeah, this is illustrating here that it doesn't detect anything when it's just plain expression. Is that right? What I'm trying to say? No, I think it was somewhere below. Anyway, but yeah, you just have to turn it into expression instead of string. Okay, so here's the functionality that it's getting somewhere near what we want. So basically, I have here an sgraph tagged with the
Yes, with the
combinator
SDK
rewrites,
rules.
and then
Yeah.
here you basically say, well, this particular syntax to say that whenever you write the nodes, your states, you do a motif detect, and in this case it is just detect A, whatever happens, and you start with this particular combinator expression,
Hmm.
and that's what it outputs. An interesting thing that I need to know is that this is a graph and this is an image. I guess it's very relevant for when you're dealing with the actual data. But this is very nice because you have the legend, which is amazing. I think it's very visually appealing to have that.
Oh yeah, Nick, I've encountered difficulties when
Right.
trying to create legends for nest graph tagged. All kinds of weird things where the images get cut off and the images get cropped and you don't see the full thing.
Yeah. But well,
Yeah.
but
Well,
at least
it's
it does what it's supposed to do.
legend is just an ad hoc
It is.
thing that just been added to the graph.
Yes.
I'm
And then
not doing
you
anything
take
special.
and it creates a graphic, right?
Yeah, well, it's even a simple graphic that you can just
Yeah.
take apart
It's
to
fine.
these
Yeah.
components.
Yeah.
You can extract a graph and a legend separately if you
Yeah.
want.
Of course,
Very
exactly.
easily.
Yeah. I know. There's no issue. Okay, so here's where I was losing my mind because I mean, it was such basic syntax.
Why?
But no, it was just basic syntax. But this symbol here, for some reason, when I copied over from one of your notebooks, it was read differently on the cloud compiler, and it was not. It was giving me error, and it was such a simple syntax that I mean, I didn't ask. I mean, I solved it after some time, maybe not hours, but like, but it was
What did you have? What did you have to do? Did you just have to retype it?
retype it with my keyboard and locally. Yeah.
Yeah.
Anyway, so
What was it being treated literally as less than or as opposed to just setting up an association?
I have no idea because it actually was highlighted in purple, so it was being recognized as something functional, but I have no idea. Anyway, so
We need to collect such things and then just file a bug report to the
File
code.
bug reports. Yeah, right.
Yeah.
right. Anyway, so okay, so what's the point? So remember, I said rewrite systems is a very general thing, but what about
Yes.
combinators? So let's very briefly regard combinators as a rewrite system. So this is the multi-way one, which just displays this more parsimonious sort of plain-looking graph. And bear in mind, this is just a particular case of a rewrite system. I mean, these are examples that you've seen
Yes.
before. And you can enter other kinds of combinator-like rules, and you get similarly some other confluent systems and things like that.
Sure. Different kinds of rules. Why not?
Yeah, I mean, this is some notes to self. This is mostly a note to self that these two graphs are the same, whereas, I mean, despite there being an extra A here, basically, because there's, you're rewriting something and it just stays on the side. Sorry, there's an extra A
Yeah,
here.
isomorphic.
Note there.
Yeah.
Yeah, they're isomorphic. However, these two expressions look terribly similar, right? This code here, the only distinction is that there's a space here or not, right? So this thing here is a space A.
What does the space do?
The space basically, this Nick told me this. So this is a different symbol. AA is a different symbol. Like Wolfram language just considers AA as a symbol of its own, which is not A.
So I've never seen an expression in combinator form that doesn't include the
Yeah, but
are
this
they
is
braces or are they brackets? I'm so sorry, Nick.
Well, space there is a space anywhere in any expression.
in any expression. This is just
multiplication.
Wolfram language expression. There's nothing combinatorial.
It's multiplication.
Yeah, it's
If you have a space there, it's just multiplication.
Yeah, it's basically juxtaposition of symbols in the language, and if you put them together, then they make up a different symbol, right? It's like a name for the symbol. Anyway, so and it's reflected by the very different topologies of the rewrite graphs, of course.
No, but shouldn't we always use brackets? I mean, if you have two, I've never seen any S or another S or a K or another K or S or K or K or S. It's not separated with brackets in typically.
But what do you mean?
What is this black magic here, where you just have you have these naked symbols right next to each other without some breaks between them?
Well, it's just Wolfram language. It's a Wolfram language expression.
This is like it's like a caution for every programmer that you should treat this as an expression too. Like if you print a full form of this expression, you will see that it's another head called times for multiplication, right? And you can treat times also as a symbol and as a combinator in this sense.
Mm-hmm.
Does that mean
just
that
expression?
Does that mean that A space A, you would just treat that as you would treat that as A times A, but you would just treat that as you would treat S?
No.
As a
S? Why S?
Well, what is it?
Well, there's no rule.
Is it
it's a completely inert under this set of rules. It's a completely inert head, like this multiplication.
Sure.
It's not going to read into anything.
Right.
But
it's just an inert sub-expression.
When I say S, I don't literally mean S with the S rule. I just mean it's not like you're incorporating the times operation into the rewrite. It's just that A times A or what have you. This is just I suppose this is just another piece of plaque that just kind of it's like a barnacle that'll be attached to every expression, and you won't be able to do anything with it. It's just going to stay there.
Yeah, that's exactly what the graph shows. I mean, if you look at the states, there's an A that is just. I mean, I like it because it's just juxtaposing symbols. It's great. I think it's good basic functionality of Wolfram language expressions. It's just union of symbols. It's good. Anyway.
Okay. So you could.
It's a tree. It's a tree. It's just an expression tree.
Yeah. Okay.
Formatted nicely.
So this we covered before. Okay. So now the point of this. So these are combinators. This is a particular case of a rewrite system, and now we want to think about emulating them. Okay. So this is the conceptual summary of what I think I'm trying to do in this project, and what I think is a sensible thing to do, and the basis for the experiments that we want to run. So combinators and Boolean algebra, they're both rewrite systems. So as formal systems, I mean, James said, and Stephen wrote in his writings about how combinators are somehow more fundamental or more parsimonious, and you can definitely argue for that. But if you just forget about those analyses, not saying they are invalid, but they're saying just forget about that aspect, they look the same. I mean, these two systems look formally the same in the sense that you have some symbols, you have some rules, and you apply them, and you do rewrites and you operate. So the question is, are these two systems related in some meaningful way? And this is what we mean by emulation. And particularly, I mean, and this is exemplified by a real example on the diagram. I mean, the actual graphs are not real; they're just schematic. But I guess the one on the right is real.
Point.
But the point is, if you have two states on the right, on the Boolean algebra side, so say true and false, right? That can get rewritten thanks to the first rule that I wrote there. Can get rewritten to false and true, and that obviously evaluates, which is another of the rules, if you like, evaluates to false, and so it evaluates to zero. But you could also evaluate something that is true and false, and you come from a larger state into that. Anyway, so there's this massive network, right? It's sort of the sub-Roolead of Boolean algebra in some sense, right? The slice of the Roolead that just corresponds to Boolean algebra. And same is true for combinators. So you have the same sub-slice of the Roolead that corresponds to combinators. And the question is, well, Stephen figured out, or at least it was in his writings, this correspondence that you can emulate Boolean algebra by assigning. And the assignment really is directional, right? You say, I send 0 to be represented by sk, and I'm going to read it off.
Yes.
So in that dashed line, there is information that we are not directly putting in our algorithms immediately when we do the computations, right? So that's why I wanted to have these conceptual sort of frames, like this is what we do, and then all the functions need to serve this idea that is sort of at the basis of the experiment. And so the question that James just pointed out, and then we can get into the nitty-gritty of the function after this, The question is then, if you have these two states, for example, on the Boolean algebra side, false and true, true and false in this way, and they're related by these particular rewrite paths, then obviously if you can emulate it on this other side, they will be computed and they could be connected for sure, because we know how combinators work. And so the question is, what is the relation between this, for example, the path homotopies, or the length of the paths, and basic questions about paths, right? And in particular, whether there's intermediate states in the combinator side that correspond to states in the Boolean algebra, and more generally, like Nick pointed out last time, perhaps substructures that correspond to sort of emulations of some structure on the Boolean side, right? So it might be that the precise terms are not necessarily Boolean algebra expressions, but they might be dependent from them, and they might be arising from them. So with that goal, I try to develop this, and let me show you the function in action. So this is one of the problems. This is not doing any better, but this is the start of it.
Wait. What is that underneath? It's nest graph tag. Okay.
Yes, nest graph, but
okay.
It's trying to detect whether commutativity of interjection of and is evaluating to true contains an instance of or. And I don't think, you can really see that, but I was just making sure that this works. And so this is the beginning of it, right? Just by checking with K, which obviously is going to happen because everything is S and K. And you can see, this is what the functionality would do, right? I really couldn't really render anything else because it was and this is so pixelated that it's pretty worthless even to have. But this I think is the functionality that it's ready to be implemented, and which can just start to spot patterns and maybe color. We can
just your
color versus
your legend is a little bit off, right? Because it not.
Oh yeah, that's true.
It doesn't always have two colors for two types of rules, because each of the rules can also have multiple outputs depending on multiple positions that it can act.
Actually, that's something.
So that's why there is more than one, more than two.
Yeah, that's something I wanted to understand, because what is happening there actually? Because we only have two rewrite rules, right, for combinators.
Well, yeah, but two rules, but each of those can act in multiple places.
Of course, but they are the same rules. So I thought that the color labeling was according to which rule was being applied.
Well, it depends how you constructed it. The way this multi-place works is you're just outputting the association, and with keys, and keys contain the index of a rule and also a position. But they kind of have this uniform list. Like in the first example, if you just run it for one step, you have 3 arrows, right?
And you can
just go back.
In this example, this is a fine example though. In that example, when you're doing, if it's just n plus or n times, there's only one way to apply each of the rules at each step, right? You have some number and you're either going to add 2 or you're going to add 3, and so you can label those respective applications of the rule easily. But in this case, it seems like every single application is getting its own colored edge. It's not just 3; you actually have 4.
It's one application of the replacement of the multi-replace function. It's only one application of that function, but the number of outputs depends not just on the number of rules, but also on how many places each of those rules can act.
Oh, that's what I mean. When I say the application, I mean the application in different positions.
Yeah, exactly.
Yeah. So okay, but just to begin this though, I would recommend that we begin with the single way case where yes, we should consider all of the different applications at different positions, but we should begin with something like this, and highlighting. I mean, the key first analysis we want to perform is to what extent are all of the Boolean, basically we want to search for all of the Boolean functions under our particular semantics. So in this case, you're looking for SSK, but I would just take all of the ones on the list, and or equals true, and I would take those and search for all of them in the single way case and see how much unhighlighted content there is for a number of different examples. I would begin with that just to build up some intuition.
Yeah, I think that's a good place to start.
Of course, one thing that I'll say also as an experimental detail is if you include A's and B's, if the rules are expressed in terms of S's and K's, if you include any other arguments, of course, those are not going to get highlighted.
Yeah.
But you don't have to include A's and B's. This whole thing can be just expressed in terms of S's and K's.
Yeah. This was one of the examples that we did, so it's not even.
Yeah, sure, right. But if you take any arbitrary Boolean expression, because the functions and the true/false values, because those can all be emulated in terms of S and K. This can just be SK all the way down. So that will be, I would recommend doing that, because if you do it with A's and B's, yes, you're going to find that there are large unhighlighted regions.
No, these A's and B's are purely spurious here. I mean, this is not. I mean, this was just the example that we copied from last time. Like the actual, like these examples are just copied from above, and this and A and B, these are meant to be variable statements, right? So obviously when you do because there's two things, right? This is something that I wanted to clarify also for the viewers, that there are two ways of doing this, basically. There's the evaluation way and there is the rewrite system way, right? So we were actually doing the evaluation way, where every check was mapped against evaluation of truth values, right? So our Boolean functions were defined in terms of truth values. You could just define Boolean algebra as a formal rewrite system, right? With all the properties.
What's the difference between evaluation and rewriting?
Well, I mean, evaluation is a particular case of rewriting. Don't get me wrong, but when I say rewriting, I mean the axiomatic rewriting, in the sense that your symbols are your variables, your universal variables, and your operators, and your rewrite rules are the axioms that the operators can satisfy.
Wait, so Carlos, if I understand the question, I mean, this is a question I've asked. I'm not sure if it's the same question.
Yeah.
When you actually, if you look at, if you take axiomatic theory and you print out the axioms that inform Boolean algebra, it's in terms of A's and B's. You're not taking particular truth values, true and false.
Yeah.
Is your question, in order to, I mean, I've thought about this too, which is if you want to express these axiomatically, where you're not taking on particular true/false values, then you're inevitably going to find that those evaluations take on this non-computable, unevaluable content, right? Because those A's and B's and C's are inert. You have to put that in quotes.
Ah, that's right.
Yeah, no problem.
Yeah. No, I understand. I understand that these are inert symbols but I mean, everything is an inert symbol unless you define a rewrite rule for it, right?
No, I was asking, does this relate to the question you were asking, or are you asking something different?
No, I think it's directly related to what I'm asking. Yes, I think.
Okay.
So yes, exactly. So the point is, I mean, these expressions here, right? These can be read as rewrite rules, right? I mean, A, B, C. I mean, this is just. Okay, these are equivalences.
Yeah, sure.
Logical form, equational logic here, but they can just be interpreted as. I mean, Stephen did this for the Metamathematics project, actually.
In the Metamathematics case, yes, especially when you treat these as variables, you can perform rewrites on them. In the combinator case, right? But in the combinator case, if you have the S and K rules, if it's not an S or a K, it's just a barnacle. It just sticks there and it doesn't do anything. I don't know why I'm picking this barnacle metaphor.
It's the same as here. Here you have this
but not
all the
really.
circle plus and circle times, right? Those are the same as S and K combinators. In terms of rewriting, it doesn't matter.
No, of course, but the point is, in this case, A, B, C, they're not true or false. They're just these variables. And when you do it in the combinator case, unless you actually assign them some sort of truth or falsity value, by making it in our case K or S of K, then they'll just be A, B, C, and nothing will happen to them when you actually evolve the combinator to a fixed point. And your fixed point will probably just be some garbled, mess of A, B's, and C's, perhaps with a few lonely S's and K's kind of mixed in.
So let me point out that, and this might be the reason for this comment might be that we are implementing this in Wolfram language expressions, but in this implementation of combinator rewrites, actually any symbol that you throw in, it's going to be meaningful in a sense that it could be sort of a sub expression, that it could be sort of like a placeholder for a bigger sub thing, and it's going to rewrite it accordingly, right? So it's not going to treat it as garble. It's going to treat it as this is part of my system. It just has a name that it's in some bracket, it's in some position in the tree, and it's going to rewrite it according to the combinator rewrite rule, right? Because the combinator rewrite rule has these generic variables x, y, z, right? So those could be anything.
Yeah. In this way, there's no difference. You can even ask for axiomatic theory for combinator axioms, right? You have it right there.
Is it there?
Just to compare it.
Well, but what I mean is this. Look, if you do this in terms of S's and K's, or sorry, specifically in terms of K's and S of K's, right? If you plug that in to some Boolean expression, it will reduce down to true or false, to S or S of K. As soon as you put some A in there, you're never going to get down to K or S of K.
Correct.
You're going to have, if you have some A in there, you're going to have maybe a few S's or K's, but it's mostly going to be, A's. And that's not interpretable. It doesn't reduce to anything that has meaning, so far as I can tell. And this is an interesting experimental question. As far as I can tell, as Carlos showed before, you can map the initial condition and the fixed point, so to speak, between your Boolean, I don't know if you want to call it a category, and your combinator category. You can kind of map the start and the end points. But if you just include some random A or B, it's supposed to be a variable, those fixed points don't seem to resemble true or false at all anymore.
I agree.
That's my key point.
I agree with that. I absolutely agree with that. I was just pointing out something more general. Like I was not disagreeing with that point.
Oh.
Yeah.
Oh, okay. Wait, what's the more general point?
No, the more general point was that at the level, I think it is what Nick was saying as well, is that at the level of how Wolfram language in particular treats this. Because this is something that we shouldn't, I think we should be very careful to, especially for people who are not familiar with the language, including myself, which I'm a good test case. I think we should be quite careful of what the language does exactly, like what the computation actually is. And that's why I was so insisting of like, okay, this is the idea that we try to capture, and we have different options. And so when we implement expressions in Wolfram language, which are essentially typed trees, right? These do some things, but not everything, right?
Right. Well, so I think the point is, if you add some A's or B's, you could still compute kind of over them.
Yeah.
They're still going to get swept. They're still going to get kind of swept along. The thing's not going to break down.
Yeah. I'm arguing that we should have A's and B's. At no point I'm arguing that we should have A's and B's. All I'm saying is that the framework for it is equivalent. That's
right. I'm not saying that I'm not asserting that you're making that assertion, right? But the key point is that if you include A's or B's, you can compute over them, but they're not on the left-hand side of some particular rule, and so they themselves will never you can never pick an A as a position for the application of a rule. You'll pick some S as the application for the rule, or a K as the application kind of position, and it can sweep up these A's, B's, phi's, xi's, digamma, kappa, whatever, and it'll sweep those up, but that will never be the position of a rule because it's not specified as the left-hand side of some rule in the rule set. Yeah.
So Nick, to answer your question, this is what I mean. What? Okay, something happened. So a tree. So it's okay. A labeled tree. Maybe I shouldn't have said type tree, but like labeled tree. That you have your nodes that are labeled.
Well, I wouldn't call them labels. There's no difference between list and A and B's there.
I agree.
Those are just symbols.
But they are symbols. That they are different. List is not the same as A, right? As a symbol.
Well, they're different, yeah, but I wouldn't say it's like some kind of type.
No, I agree. That's why I retract the type language, but I would say it's labeled, for sure. Because I mean, if you say a tree,
yeah, sure.
Yeah, I mean, if you just say a tree, then clearly you can't label your stuff because a tree doesn't have any structure in the nodes.
Yeah.
Yeah, that's all I meant.
You even have an unlabeled tree function. That kind of.
I mean, the graph function is unlabeled, right? At least outwards in the language.
No, even the trees can be easily unlabeled. There's like unlabeled tree function, just removes all the labels.
Sure, and it becomes a graph, right? Just a graph.
No, it's not a graph. The difference between tree and graph is that a graph doesn't have any order of its children. Trees has ordered children. That's the difference.
Okay.
So even if you have even if you have a graph in the form of a tree, it's still not the same tree as like when you order all the children.
So, at the level of the data structure, right? Yes, I agree.
Yeah.
I agree. Yeah.
That's why we kind of have both trees, but trees when you order your children are more useful.
Yes.
Because they actually represent the same thing as expressions.
Just on the point of language, internally, Wolfram language does label the vertices of a graph in order, right? It chooses some labeling, doesn't it? Numerical.
No, the vertices, the list of vertices is some sorted ordered list.
Yes, that's what I meant.
For example, if you ask for an adjacency matrix of a graph, it has to pick an order of of your rows and columns.
Exactly. Yeah. That's important to know because that's not the same as in mathematics. Like in mathematics, you have a multi-set of vertices.
Yeah.
Exactly.
But anyway. But the graph structure, the graph shouldn't be dependent on that.
It's not dependent on that.
Order vertices.
It's not dependent on that. Yes.
But it's kind of very implicit there.
Yes, exactly. No, good point about notation. But yes, going back to James' point. So, what I was trying to say. Again, I completely agree. I mean, we are doing the emulation, and this is going back to the orange assignment, sort of the functor-like thing that I drew here. This orange stuff. The orange stuff is meant to be something that we understand, that we are not going to, at least the first experiments that we perform, like the one you just suggested earlier, those are not going to include the orange information. The experiments are just going to be some stuff happening in either side, and we're gonna display what happens on this side, and we're gonna detect what the orange dots we will detect, but the program itself, the algorithm that we built, at least the first ones, will not incorporate the information of what it means to send things via the orange, beyond the fact that there's a motif detection that corresponds, there's a motif correlation. Beyond that, there's not going to be. But there's a lot more to that, because we have to say this motif corresponds to this other and not this other, because K's appear everywhere, and so is true is everywhere, right? And false is everywhere because it happens all over the place. But that is meaningless. That's certainly not what it really should be, right? So that's what I mean.
Yeah, right. So I mean, so what we could do, we can just do it right now, and if this won't evaluate well, we could pass it to Nick. I mean, what I'd suggest is let's find a nice, healthy combinator that evaluates them. It takes like 10 steps or something to evaluate to a fixed point. And let's search. We won't search for it's. I mean, so it's first and last, I believe. When you're treating them as Boolean operators rather than true or false. But we won't search for those. Let's search for everything else. and let's just run a few of these in the single way case,
Yeah.
and let's just see how much unhighlighted content there is. I'll be interested in seeing that.
Yes. I could attempt to do this, but it will be slower. And because we are a bit late,
No,
I would just pass it to Nick.
Pass it to Nick.
Okay. So while
This
Nick,
is when having one of those intermission graphics would have been nice. I can make one.
Oh,
But
yeah. That's easy.
I should just have Carlos, I'll give you one, because they're easy to make these title screens.
Yeah.
Oh, Nick has a nice plant. Oh, that's nice. Is that real?
Doesn't
No, it's not.
doesn't look like real. Even at this resolution, you don't fool us.
I should get a plant.
I have a
So what are we
plant.
doing? Should
Look at this.
Should I take Carlos's notebook and do something with it?
Yeah,
We can start it from scratch.
It's an actual
we
bulldozer.
take sorry, I'm two things at once. Yeah, that's a cute plant.
Yeah.
Okay, yeah. I mean, let's open. Yeah, I mean, if you want to do a fresh notebook, and then take whatever functionalities in that one that Carlos had, and yeah, let's just take a few of these, evolve the combinators, and highlight without first and last. Highlight everything else: XOR, NAND, implied, et cetera, and let's just see. Maybe we can just run through a few of these. Let's see if anything pops up.
One
We don't have
comment
to
that I
take
said
bets or
last
anything.
time that I think is still relevant is if we just evaluate, if we just do the evaluations, right, the truth value evaluations, like we did last time, we should not be able to find any, right? Because if we do, then something went wrong or something, or I don't know, or my intuition is completely broken about it. Because if the evaluations are is the defining, I mean, that's how we define the Boolean functions, right? We have the Boolean values, the 2, 1 and 0, and we define them as matrices basically of Boolean values. So evaluation just means one step in the Boolean algebra sub-Ruliad, right? It just means one step there. So if we find any, I mean, it means more than one step on the other side. We already checked that. But if we find something inside there, I think it's going to be very strange. But I'm not saying it's impossible.
Yes.
But
Well, right. I'd like to see just if there's anything, and if there's not, then
that's a
I mean
result
that's
as
what
well.
I expect. I expect for the most part there won't be anything, and if there is something, it's not clear. I mean, if I had to give out, let's say we find some stuff, and like
Okay.
we find some Boolean functions along the way. Whether or not it's significant is another thing, because you could say, well, it's just the case that you're applying these SK rules at different positions, and every once in a while they happen to give rise to what corresponds to Boolean functions, but that doesn't mean anything.
I will say more. Because this is what I said. The full comment from last time is as follows, and I wanted to express it in the drawing, but it was a bit too complicated to draw on top of everything. If we have a derivation path on the Boolean side, that derivation path is going to show up in the combinator side. Because it's just by induction, you can argue that this is going to happen.
Because there are actual steps
Yeah.
in the Boolean category, basically.
And
Right.
and that's why I think one of the first thing I'm going to do, tonight, before I go to bed and let it run it, is check for all the evaluations and check for all the possibilities of the Boolean function, of the combinator emulations that could happen within just evaluations. Because if something happens, let me put it this way, if something shows up there, then we are in for something strange and something that is not intuitive. If nothing shows up there, then we can still, the question is still meaningful to ask for longer derivations, how they navigate the combinator space instead of the Boolean space. But but things are going to be, it's going to be much more complicated to assert that something is unexpected, because we will have to do a massive search that is covering systematically all possible expressions and derivations on the Boolean side as well as on the combinator side. And I mean, it just will take longer. I mean, I'm not saying it's harder. I'm just saying that it will take a longer search.
Can you explain that one more time?
Yes.
So are you trying to find, okay, so you're trying to find examples where on the Boolean side there's just one trivial step, or where there are several steps on
just the evaluations,
on the
right?
side.
Just the evaluations. So just the basically the matrix, the Boolean matrices that define the 16 operations, right? And those have some non single step expressions in combinators already. We saw that, right? At least most of them.
Yes. Yeah.
So what I'm going to do is I'm going to search for those, for all the possible combinations and related combinations. So I'm going to do sort of like parent, I'll try at least to do parent search to see if anything ends up there from just the basic definitions of the operations. Because
wait, so if I understand what you're saying, actually, this might not be what you're suggesting, but the point is, if we take and true in combinator form,
mm-hmm.
Is this what you mean? That we know we can recognize the actual execution of and,
mm-hmm.
for instance, and so if you know that for each of these, then you could try and recognize those when you have some more complicated evaluation. Not just the actual presence of the Boolean operation, but you can see these things being evaluated in time at different positions in the overall evaluation. Is that the point?
Just to double check that what you just said is what I meant. What I meant is, if you have an expression like and like you say, something that you could write in combinator form, and because in combinator form it's not a normal form, you can still operate on it, right? So you can still perform
mm-hmm.
the rewrites. That might lead into things that are gibberish for the Boolean algebra side, but they might be sort of unique to the initial state, right? They may be unique to the initial state that is meaningful in Boolean algebra, but it might sort of descend into some combinator gibberish, and that's what I'm gonna try and pack up all that gibberish, and I'm gonna search for that as well, because if that, I mean, that means that you come from an emulated Boolean algebra expression. It's not that you are a Boolean expression itself, but you come from one, and I think that's still relevant.
I see. So you're saying that perhaps in some simple cases, given some nice emulated Boolean expression input, you might get some unrecognizable output.
Mm-hmm.
But if you just treat that as some machine encoding of the output for this, you can then take that and then you can try and search for that too and see if that shows up regularly.
Yeah.
And if that shows up regularly, then it's like, okay, this gets kind of encoded down to something that's less recognizable, but you can still find it. If you identify it and then try and search for it and you don't even find that, then it's like then that's quite bad, right? Because then it's just like it just continues to get encoded, and you can't even follow the encodings.
Yeah.
More or less, right?
Yeah, that's the basic idea.
Good.
To search for
this. That's good. That's interesting. Okay, now we're doing that thing where we talk while Nick is presumably doing something in the background, like thinking about his next plant to buy, or doing something in the notebook.
Yeah, there will be infinite amounts of ands of multiple lengths.
Yeah.
Yes. So yes, there will be infinite amounts of ands. So this is always going down to normal form to be able to do something computational.
Another thing to look for is when your motifs have like multiple arity arguments, right? So you can, because how does that original table for Boolean combinators was discovered. We were enumerating all of them basically, right? Until we find the correct Boolean table. But searching for in this manner for higher arity Boolean functions is not very efficient. But maybe when you look at the sub-expressions or motifs in the like intermediate steps of any particular combinator evaluating, right? Maybe or some high arity sub-expressions. Maybe they represent already some high arity Boolean functions, and we can compute Boolean tables for those.
Did you bring up a similar point during the last meeting?
It's a little bit different. I think last time I suggested we just run intermediate steps as they are, right? As a whole, not sub parts of it. But now I just, because last time we just figured out that it's always some trivial thing like last or first. It wasn't very interesting.
Yeah.
So now we're just suggesting, instead of that, we just look for motifs and do the similar thing.
But I guess it's going back to Carlos's visualization. It's like we have some particular, that mapping. It's some particular encoding of, it's under some particular emulation regime, coding regime where we're saying, this is true, this is false, this is, and we're kind of defining all these things. And it could be the case that the intermediate expressions could be Boolean emulations under some different interpretation. But then as I would see it, you would have this combinator category, and then yes, you could map all kinds of different categories and say, yes, this is NAND, a non-minimal 4-arity version of NAND. But then you're just taking a number of these different, I don't know if you want to call them semantics or encodings. You're taking a number of these and then you're mapping them to this particular combinator category. And I'm not sure how helpful that is, because ultimately anything could be a non-minimal or different.
Well, at least we can eliminate a bunch of those.
So,
for example, in our example where we have false and true as k and as a k, right? We can.
Yes.
All our Boolean combinators usually evaluate to those, right? If you just provide true and false as its arguments. It does, yeah. So it does mean that all intermediate expressions is some form of true and false already. So so we can just run all our Boolean functions with all possible arguments to them and just record all the intermediate steps and just call them whatever they finally evaluate to its normal form. Like all the intermediate steps we call true or false. And those we can particularly eliminate from our search. Because under like combinator evaluation, those would be equivalent. And then we just search for other expressions. Try those as true and false for the intermediate motifs. Yeah.
What do you mean? What do you mean when you say try them as true and false?
So like take any from that table. Let me share this table. All right.
Yeah.
Mm-hmm. So when we have this table, what is the most simplest thing besides true and false? It's like AND, right? So AND of true and false relates to something like true and false. And there are some intermediate steps.
Yes.
That we can.
Yeah,
therefore
like
also should treat as
like
true and false, right?
Yeah, I think maybe 2 or 3 intermediate steps. Yeah.
For example, if we take this S and hold on, what is the language? S like K is our false, is S and K is our something like that, right? Well, it doesn't matter. So this is already, because we know that it's going to evaluate to false. We can call this also false, and we can do for all the intermediate expressions too. It's like we can evaluate this combinator once. There would be a new combinator, which is not a normal form yet. We can also call it a false, and then we can search what combinators left, and only search those alternative Boolean tables of functions among those combinators.
Wait, let's go through that more slowly. So you begin are you treating this as an initial condition, or is this just something that we find within some intermediate expression?
No,
This
if
this for
we
this particular
if we have
example.
one, if we're gonna set one goal to find all possible tables like this, when we have true and false with some kind of encoded as a combinator, right? We can at least find all the equivalent forms of this table by just evaluating a bunch of functions on true and false and calling for true and false as intermediate steps there, because we know their normal form already.
But we're still keeping K as true and S of K as false.
Yeah,
Those
that's
are
just
staying.
the one version. That's like the most basic version.
Sure.
But there's also a bunch of equivalence classes that all this table provides, basically, right? So, and the point is to find alternatives to that.
So your point is, well, wait, no, what's your point? Is your point that if we fix K as true and S of K as false, and you find okay, you have some intermediate expression, and you have something that will evaluate to true or false, you can find in some equivalence class other combinators that will also evaluate to true or false, and that there's. But what do we do with that? We find other.
Well,
other
we just call it an
evaluate true or
equivalence
false?
class for this particular one. Then we try other, like we switch true and false. That's another table of functions that you can
But wait,
find.
Nick. What are you proposing we do with the equivalence class? So let's say we have and true, which evaluates to true, and that's somewhere in some intermediate expression. So we know that evaluates to true. So in the equivalence class, is this another combinator for and that evaluates to true, or is it just any combinator that under this regime of K is true and S of K is false evaluates to true? Is it anything, or is it specifically another and combinator that also evaluates to true?
Oh, okay, I lost you there.
I've lost you a little bit too. Nick, what do we actually do with the equivalence classes? So I agree that there are some equivalence classes, but what are we actually doing with them?
Well, the point,
proposal.
The overall point here is to find those in the motifs, right? There's no, because we have just a small table, it doesn't make sense to just look for this kind of functions, right? You have to expand our search.
But the equivalence class is infinite, probably, right?
Well, maybe up to some certain size, it's not.
Okay, but my question is this: how are you defining equivalence? So let's say you have and true, something like that, and that evaluates to true. What else is in the equivalence class?
Well, this one, basically we call it later point list. Right. So all of this and all the intermediate ones we call is an equivalent class of combinator true. Right. And everything that evaluates to K in the end is basically equivalence class of true.
Even if they're different Boolean functions, you're not distinguishing them by Boolean functions. It's this.
No,
this
there's
one
no
happens
functions.
to be
As soon as you apply it to the arguments, and it has a normal form of true, it's true, right?
So you're saying it's just any list of S's and K's that evaluates to true. These are all in the same equivalence class. They're all just mapping to true in the end. Yeah.
So if you're looking for a motif and it doesn't relate to true and false, it makes sense to search for something like not in this table. Right, we have to search for another equivalence class.
Yeah. So can I maybe rephrase what Nick you're trying to say, because I need to go back to your train of thought. So your proposal is basically a systematic way of finding equivalent emulations of Boolean algebra with combinators, right?
Oh yeah, in order to classify
Yes, yes,
all
yes.
the intermediate steps.
Yes.
In terms of those.
Yes.
Yeah.
So something that would be very useful for me and probably anyone watching, and perhaps even James that is also a bit lost at this point with the train of thoughts here. I think if we saw explicitly how one of the functions, say like the one you just said, James, like and true, if we saw the exact syntax of what evaluating means, then it will be.
Oh, that's what it is.
No. What I mean is, like the expression. I mean, is the expression? I mean, and is a binary function, right?
Yeah.
So.
Well, in this case, it's a combinator.
Yeah. So do you? So the question is, do you pass that as a head to something that has two arguments and then just let the combinators do their thing? Is that how it works? Because I have not seen it actually.
Well, yeah, that's what you do in order to.
Yeah, I mean, I'm not disputing anything.
Table,
I mean, I'm not disputing anything. I'm just asking because I don't know, right? Like
It's like, yeah. For example, if you wanna try, for example, let's make all the tuples of those true and false combinators, right? This is all possible inputs to binary Boolean functions, right?
Sure.
So, for example, if you apply like AND, but carried version, I have a uncarried version applied, right? So this is basically 4 values in the Boolean table for AND, right?
Okay, so
and we know the values,
right?
And we can run this combinator functions on all those, right? Make a clone requirement.
Yeah.
Right. So basically, this is like a bunch of equivalence classes. Like this is just 4 versions of for true, right? And there's a bunch of new versions for false, right? Because all of those are false, basically, because all of those have normal form.
So, but Nick, just to zoom out for a second, is the goal to find more combinators that are in this equivalence class, so that when we're highlighting, we also search for these two, and we see taking the equivalence class into account. Taking the equivalence class into account, your kind of hypothesis, I'm guessing, is that taking those into account, we might find more content to highlight. I mean, do you think ultimately everything, all of the intermediate expressions, if you perform this equivalence class search far enough, that everything will be highlightable eventually, because you are able to get all the way down to true or false in the end?
Oh, it would be interesting if everything is going to be highlightable.
Yeah, this is the open question, right? Okay, this is science. Yeah.
No, I think
I don't know either.
Yeah, I mean, I think I definitely can start running some of these, and another thing I'm gonna do is I'm gonna try and clarify the meaning of emulation in this context, because this is very up in the air. Like probably Nick understands exactly how it works. Probably Steven does. I don't know, James, if you do. I don't. I mean, I don't know what emulation means exactly in this context. I conceptually I have a good intuition of what it is, but I'm gonna try and really nail it down and make it operational, so we can make much more rigid. Because this entire conversation about equivalent classes, I don't think we I mean, I agree with the fact there are equivalent classes in this sense. I completely agree with the perspective, but in a sense, I think we should constrain our computational system such that those classes do not exist anymore. Like, we should be able to find like a slice where we can ask the question in a computationally bounded way that is, because I mean, at least conceptually the question is completely clear. It's like, can you, it's just path homotopy between two different graphs. I mean, mathematically at the basic level, that's what's there, and so it's just a matter of how we define those graphs to begin with, because those graphs are defined by this sort of sections of the Roolead, which are all the possible initial states and all the possible rules applied to them. But in this case, all the possible rules, meaning the ones of the rewrite system under consideration, right? So I'll try to make that super precise while I keep on doing the first tests that we discussed with highlighting.
Hey, Carlos, so when you say you want to understand emulation
in this context
more clearly, I mean, does part of that mean understanding how we actually got these different combinators in the first place, for instance?
Yeah, that will be part of. I mean, I read 2 weeks ago or 3 weeks ago when you told me that this is going to be the starting point. I read the post, but yeah.
But no. What I mean is like how these were actually obtained. Like you'd have to read the code in order to understand how we got these. I mean, is that what you? Because that's like the fine understanding of how we know emulation. These emulations. This is just the result of that particular search.
I mean, when I say understanding, I don't really need to. Once we have them and once I know exactly how they operate, understanding just means, delving into what the consequences of that is. I don't really need to know exactly how they were found. It's not. It might be informative for later, but for right now, like I don't really need to know exactly how these were found, because they work, and that's the point. I just need to. I think I need to. At least I have to do it. I have to really understand in this context what emulation means, because especially there's the confusion of last first being the same as the truth values as well. That's another point of confusion. And the reason why I was bringing up this picture of two rewrite systems that are kind of at the same level, but there's this emulation relation, is because you don't need to evaluate things. You can sort of circumvent evaluating, and you can just think of abstract rewrite all the way in both sides. But I will work on the evaluation side, because this is the one that we have already. So I will work with this for a while, but I have to really understand what it means emulating here, and I think it's going to benefit us in that we're going to have much more constrained computational questions to ask once that's clear. And the good thing is that we can already start to try to find some patterns, right? So we can start, for example, the evaluations. I'm going to map them out. We can see some patterns. So yeah, it's exciting stuff. It's coming together.
Cool. Well, I think we should have another conversation about this really even this week. Maybe just a shorter meeting that we, some additional live stream that we can add to the calendar. Because my basic stance on it usually is if we all have a very clear understanding of what needs to be done, and then people just need time to go do it, and it's like, okay, great, we'll chat next week. But there's some kind of open conversation that's going here. We should probably continue it before we all forget what we said, especially since we don't have a project manager taking notes or anything. So we're all just memorizing.
I'm definitely taking notes. Well,
are you taking notes live? Like, do you take them during the live stream?
Well, I have some plain text notes.
Okay, that's
I have
cool.
like
Nick,
300 windows open here.
Nick, are you taking notes?
Oh, not particularly, no.
No, I'm focused on the conversation.
I'm taking notes of saying, when we said, oh, this is an interesting thing, it's like, okay, no, it's just like 3 lines, whatever. But
yeah, that's good. No, that's good.
My point is,
I haven't been doing it.
I agree. I agree that we should meet soon. I was just saying that for me to be able to meaningfully contribute to this conversation beyond, I ran some of these experiments and I saw these patterns, I have to really understand how this emulation works, and so that's going to be my priority, because otherwise we can talk again, but I'm going to be at the same point, and this can happen in a couple of days for sure. Like, it shouldn't be that hard. I just have to really understand it, right? I'm not saying, I'm going to take a few weeks. I'm just saying I need a couple of days to just really understand this stuff, and we can meet this week for sure. I agree.
Okay, cool. Well, should we summarize? So just a few summaries. So Carlos is going to, there's some further kind of understanding of emulation to be done, and there's some initial searches that can be done I strongly recommend beginning with the single way case,
Yep.
and we can do the kind of initial search, which will probably be it probably won't bear much fruit. And when I say fruit, I mean you can try and highlight, different emulations of Boolean expressions and see how many Boolean functions appear in the intermediate steps.
Mm-hmm.
It's unlikely that many will appear besides first and last if you eliminate first and last. And I think you were saying, if it's the case that you pick some Boolean expression, which even on the Boolean side involves several steps, I mean, those are probably better ones to do, because then perhaps, because this is what you want to know, if there's some if it's something that involves expressions that include some parentheses, for instance, and there are several steps that are involved in the Boolean evaluation. I mean, that would be a good original test, right? Which is, we're doing it single way, and we want to test to see if the expressions appear in the intermediate steps that also appear in the intermediate steps on the Boolean side.
Yeah.
Now, there's some argument to be made that doing this single way is really not adequate, because when you do it single way, there's nothing neutral about it. You're picking particular positions on which the rules are being applied, and it could be the case that you have to try you have to actually look at many of the different paths in order to find that particular Boolean expression highlighted.
But at least for the evaluation, it's going to be quite simple. So I can do the multi-way one for all the evaluations at least. So that one at least can be done. And if nothing comes out of that, then we can expand. I mean, that's going to take, I don't know.
Well, one thing we could always do is, I mean, my main concern is that you have these multi-way systems where the states themselves include these long expressions, and there are many steps and there are many paths, and it becomes kind of unwieldy.
But you can just collapse the expression and just mark it if there's a hit inside, and then you can render it or something. I mean, you don't have to render expression.
Yeah, that's fine.
And the evaluation ones are real small.
Yeah, okay. Okay, if you want to do it in the multi-way case and just highlight the vertex if it includes a hit, that's not terrible. It would be nice though if we could take the like right now, Nick, tell me if there's something that I've missed. We can take a single way evaluation. This is done, via some particular parsing. You can take the multi-way case. I wish you could take the multi-way case and then show, well, you probably can do this, probably not that complicated. You take the multi-way case and then you fish out each in particular combinator evaluation plot, so that you can actually show, like, instead of having this
just
wild
enumerate all the paths.
Yeah,
just
but you take
enumerate all the paths.
You take one particular path and then you evaluate it the way that we do it for either as a fixed point list or as the, is it called evaluation plot? I lose track of all these combinator functions. Just the one where you actually just list all the.
You want to highlight, basically show the evaluation path, not in particular order, but in any order, and just highlight all the input outputs in there.
Yeah, right. Because so the multi-way graph, instead of showing the multi-way graph, I mean, we could show that too, and you could show, like, okay, so you have some multi-way combinator, and okay, we found some vertices that are highlighted, and then for each of those paths, you actually print the whole thing out as you would do with evaluation plot or fixed point list, and then you can actually see, which ones they are.
Yeah.
It's probably better than trying to show full combinator expressions in this multi-way tree, because Carlos had this one that looked like, it was like you couldn't see the edges at all.
Yeah, well,
I think.
Yeah. All right.
I mean, you could make. Yeah. Okay. All right. Cool.
Sounds perfect.
Cool. Well, this is moving forward. This is great. I'm gonna type up a digest. You guys probably heard about this digest. So I'm gonna type up a digest like maybe in a couple of days. And so, well, I'll be in touch, but we'll try and find some nice example of an early experiment that we can show and put it in the digest, and then we can show people, what the subaxiomatic research looks like, and people can put it on their fridge and et cetera, et cetera. So
That's
all right, guys.
Interesting.
All right, cool.
All right.
What?
No, I mean it's very hopeful that people are gonna print and put it in their fridge. I mean that's a tall order.
Well, maybe some metaverse fridge or something. Anyway, guys.
All right, guys.
Cool.
See you tomorrow.
Thanks for everyone who's watched. This has been fun. And okay, well, I look forward to seeing what the results look like after this round of experimentation. All right, cool. Cheers.
See you tomorrow.
See you later. Bye.
Cheers.